All right. Section 10.2, I think, is the simpler section. This is dealing with two population means with known population standard deviations. So again, we're just doing a hypothesis test. So all the hypothesis test steps are going to be the same. And the whole concept and idea is going to be the same. The difference is now we're going to be using some different calculator functions to assist us to get the values that we need in order to complete the hypothesis test process. So that's really what we're going to be focusing on here, is looking at the differences with these different functions. So let's look at this example, wax longevity. This is an example of two population means where the population standard deviation is known. So the mean lasting time of two competing floor waxes is to be compared. 20 floors are randomly assigned to test each wax. Both populations have normal distributions. The data is recorded in the table below. So here we've got data for wax number 1. So the sample mean number of months for the floor wax lasts. So wax number 1 lasted for 3 months with a population standard deviation of 0.33. So this is the part where the population standard deviation is known. Wax number 2 had a mean number of months that it lasted of 2.9 with a population standard deviation of 0.36. So does the data indicate that wax 1 is more effective than wax 2? Test at a 5% level of significance. So, I mean, this kind of hypothesis test, would be relevant because what if wax 1 cost $50 a gallon and wax 2 cost $5 a gallon? Well, you would want to know if wax 1 was significantly better to be worth the cost of paying 10 times more for it, right? So let's see if the data gives evidence as to whether it's actually worth it to spend 10 times the amount for waxing your floor. All right, so step 1 in our solution is let's look at the given information. All right, so the mean lasting time of two competing floor waxes is to be compared. 20 floors are randomly assigned to test each wax. All right, so we've got wax number 1 and we have wax number 2. And so 20 floors were randomly assigned to test each wax. So sample size of wax 1 was 20, and the sample size of wax 2 was also 20. Okay, both populations have normal distributions. Okay, the data was recorded as such. So the sample mean for wax 1 is 3. The sample mean for wax 2 is 2.9. The population standard deviation that wax 1 came from is 0.33, and the population standard deviation that wax 2 came from is 0.36. Now, does the data indicate that wax 1 is more effective than wax 2? So you could almost take the word effective out, and it's the population mean of wax 1 is more than wax 2. Okay, so mu1 greater than mu2 is going to be our original claim. We have a 5% significance level. So our significance level is 0.05, which gives us a confidence level of 0.95. All right. Now what we're dealing with here is we're dealing with two population means. Okay. And the population standard deviations are known, right? Because we were given those here and here. And we were also told that the populations were also normally distributed. All right, I think that's about as much as we can extract out of this word problem. So let's move on to step 2. So step 2 is to set up our null and alternate hypotheses. So here's our claim. So let's write that down. All right, so if mu1 greater than mu2 is our inequality, what's the complement? It's going to be less than or equal to. Now, mind you, other software, other questions, online questions, you might see it as mu1 equals mu2. Okay, which is a little confusing, but you might see it that way. So just be forewarned. Now, because this statement has equality, that's our null hypothesis. This one does not, so that's our alternate. And once more, the sign of the alternate hypothesis tells us the direction of the distribution, or the tailedness of our distribution. So because this looks like an arrow pointing to the right, we're going to be dealing with a right-tailed distribution. All right, so we need to keep that in mind. All right. So step 3, we want to calculate our test statistic and our corresponding p-value, which is the area adjacent to the test statistic. And this is where these calculator functions are going to come into play. All right, so it's important that you write these down and you really pay attention, to how we've labeled things. Because I guarantee you, if you don't label the values like this, and you try and get it based off of the information in the word problem and just dump it into your calculator, it's going to be too easy to get these values reversed. And if you get these values reversed, guess what? Your answer is wrong. Okay. So take the time to kind of put in the variables with the subscripts like this. Label it, keep it really clear. All right. So if you do make a mistake here in putting in the numbers, you can check and see and find out what the mistake was and fix it and move on with your life. Okay. All right. So sigma 1 is 0.33 and sigma 2 is 0.36. Sample mean of the first sample is 3 with a sample size of 20. Then the sample mean in the second sample is 2.9 with a sample size of 20. And remember, this is our alternate hypothesis here, which is going to be greater than mu2. Right? This greater than mu2 is what we've got right here under the alternate hypothesis. All right. With the numworks calculator, we're going to be in the inference app looking at a 2-sample z-test for means. And remember what I was telling you earlier about converting like an alternate hypothesis into this other form. So if we were to write, let me do this as an aside here, do this in green. So if I were to write mu1 greater than mu2, and I wanted to get mu1 and mu2 on the same side, I would subtract mu2 from both sides. This will be 0, and I've got greater than mu1 minus mu2. And notice that this form, which is equivalent to that, is what we've got here on the numworks calculator. That's the way they do it. All right. And like I mentioned with using an equal sign, the numworks calculator uses an equal sign here as well. So just be aware of that. Okay. And now we just need to put in much of the same values. It's got a different order here. It puts everything for the first sample and the first population first, and then the second sample and the second population second. So let's go ahead and fill this in. So X bar 1 is 3, sigma 1 is 0.33, and N1 is 20. X bar 2 is 2.9, sigma 2 is 0.36, and sample size of the second sample is 20 with a significance level of 0.05. All right, so let's go ahead and put this information into both calculators. So we'll go to Texas Instruments. Let me quit out of this. There we go. So what I want to do is I want to go to my statistics tests. So I'm going to hit the stat button, go to tests, and you see I want a 2-sample z-test. We're doing a z-test because we're dealing with a normal distribution because the population standard deviations are known. So I'm going to hit enter. Okay, we're dealing with the statistics. So now we just have to put in these values. So we're going to have 0.33, 0.36, 3, 20, 2.9, 20, and the alternate hypothesis was this one, greater than mu2, which for me was already selected. And then I'll be able to come down here and hit calculate. Before I do that, I'm going to leave this up because I can use these same values on the numworks calculator. All right, so what we want to do is we want to go to the inference app because we're doing inferential statistics. Okay, inference app. We want to do a test. Now we're doing a test of 2 means. All right, now because we're doing a normal distribution, because the population standard deviations are known, we're going to do a z-test. This comes later. This is section 10.1. Okay, so we'll do a z-test. All right, so mu1 minus mu2 is equal to 0. And here we want the option mu1 minus mu2 is greater than 0. So I think this is kind of left over. Okay, so that looks correct. So let's hit next. We're going to input statistics. We don't have a data set to work from, so we'll do that. Okay, so X bar 1 is 3. Sigma 1 is 0.33. This was a sample size of 20. X bar 2 is 2.9. Sigma 2 is 0.36. This was a sample size of 20. And a 5% significance level. Okay, next. All right, so here's our test statistic and our p-value. So 0.916 and 0.180. All right, let's come over here to the Texas Instruments. We'll hit calculate. We get 0.916 and 0.180. Same values. All right, so we have a Z test statistic of 0.916 and a p-value of 0.180. All right. So we do have more room, here to keep working, but I'm out of space for calculator screenshots, and I don't want you to be pressed for space. So we'll continue this here on the next page. Let me write down our z-test and p-value that we just got. Okay. And let's move on to the next step. So this is going to be step 4. So this is to sketch our distribution and calculate our z critical value. All right, so we're dealing with a normal distribution because, again, the population standard deviations were known. So let's just draw a quick sketch here. Something like that. And we know from the alternate hypothesis, this is a right-tailed distribution. So I'm going to draw a right-tailed distribution. So we're going to have a positive z critical value because the center of the normal distribution is 0. So to the right is going to be positive values of z. This area in the tail, that is our significance level, just 0.05. This region above the tail is to reject the null hypothesis. And the area above the confidence level then is going to be our fail to reject the null. All right. Now, before we put in our test statistic and our p-value, let's calculate our critical value first. So once again, to convert an area to a critical value on a number line, we need to use an inverse distribution function. So on the Texas Instruments, we'll use inverse norm. So we'll have an area of 0.05 with a mean of 0 and a standard deviation of 1. And we're looking at the tail on the right. And here we've got a mean of 0, standard deviation of 1, area on the right, an area of 0.05. That. Okay, so let's do that really quick. So let's go to the distribution functions here. We'll go to inverse norm. And we have an area of 0.05, 0 and 1 on the right. So hit paste and enter. We get 1.645. NumWorks calculator. So let's hit home. We will go to the distributions app, click OK. We want to go to the normal distribution. So notice it tells us we're in the normal distribution across the top. 0 and 1 for mean and standard deviation. And we want the area to the right with an area of 0.05. Enter. And we get a positive 1.645, same as what we got on the Texas Instruments. So our Z critical value is equal to a positive 1.645. So we have a positive 1.645. All right. Now let's see where our test statistic and p-value is by comparison. So a test statistic of 0.9, positive 0.9, okay, is going to be less than positive 1.6. So we're dealing with a z-test statistic of 0.916. That's going to be between 0 and this value. And so if we draw a line up straight from that test statistic, okay, that's clearly indicating we're going to fail to reject our null. And the area that borders the test statistic, this is our p-value. And if you look at the p-value is 0.180. And if you compare area to area, right, oranges to oranges, you can see that this area of the p-value is greater than 0.05. And that leads us to our next step. As soon as I get to switch colors here. Step 5, which is to come to a conclusion and see our test result and write our conclusion, our answer. So remember the rule, if you're going to, right, conclusion. Okay, so the rule, if you're going to use p-value and significance level, so if the p-value is smaller, then reject the nuller. Remember that? So our p-value is 0.180 and our significance level is 0.05. Okay, that is definitely not smaller. So we're not going to reject the null. We're therefore going to fail to reject the null. Okay, so that comes to the same conclusion that we get. Sorry, my laptop is freezing a little bit. Here we go. It's the same value. Gosh. All right, I apologize for that. Just kind of confuse things by overwriting stuff. And I can't move that simply. Okay. All right, let me try and clean this up. I'm sorry. What a mess. Okay, let me just erase all that. All right, so I could complain about it or I could just fix it. So let's just fix it. All right, so this is our positive z critical value. Calculated that to be positive 1.645. We have our z test statistic of 0.916. All right. And the rule is if p is smaller, then you reject the nuller. Okay, we got a p-value of 0.0 0.180. We have a significance level of 0.05. Okay, the p-value is definitely greater. So that means we're not going to reject the null. We're going to fail to reject the null. All right. And we, can come to that conclusion by comparing, you know, oranges to oranges, but then we could also do it comparing apples to apples on a number line. And so the sample test statistic is clearly to the left of the critical value. And because it's left of the critical value, that too is indicating the fail to reject the null result. Okay, now we need to couple that with what our original claim was. So what was our original claim? The alternate hypothesis was our original claim. Okay, so we're going to come here, and the alternate hypothesis was the original claim. So now with those two in mind, we failed to reject the null, and the alternate was our original claim. So coming over and going down, this is how we're going to begin to write our conclusion. So there is not sufficient evidence to support the claim that, let's see here, wax 1 is significantly more effective than wax 2, and that's going to be with a, so I'm going to put 95% confidence level. But at the same time, you could have said instead with a 5% significance level. Because honestly, the problem did ask with a 5% significance level. So you would probably want to write your conclusion with that perhaps instead. But, I think that's kind of not terribly important. All right. So that is your conclusion. So, I hope the thing that you get out of this worked through example is that, writing your conclusion is the same as before. Finding whether you're failing to reject the null and marking down what your original claim was is the same as before. Drawing this figure and comparing apples to apples and oranges to oranges to see whether you're going to be rejecting or failing to reject, that's the same as before. We used an inverse distribution function to help us get this critical value. That's the same as it was before. Step 3, we're calculating a test statistic and a p-value. Okay, that is also the same as we did before. But what's different now is the calculator function you need to use and the relevant data that you need to put into it to get that test statistic and p-value. Setting up the null and the alternate hypothesis is exactly like it was before, with a little bit of change now that because you're dealing with two samples, we may write, we may format these inequality statements slightly differently. That takes a little bit more practice, a little more exposure. And, probably the hard part now is just reading this word problem. Word problems are always more difficult, and interpreting all the given information and being able to write it in statistics language, mathematical statistics language, and then from this mathematics statistics language, realize, oh, I've got two samples. Oh, yeah. And the population standard deviations are known. Therefore, I'm going to be using a normal distribution and I'm going to be using some kind of Z test. I'm going to be doing some kind of Z test. And this is dealing with means, population means. So I better use a two sample Z test for means. All right. And I think I alluded to earlier that, what if wax one was $50 a gallon and wax two was $5 a gallon? And the purpose of this hypothesis test was to see if it's worth it spending 10 times more money for a more expensive wax. But here we said there is not sufficient evidence to support the claim that wax one is significantly more effective than wax two. So statistically, mathematically, we've shown that it's not worth the extra cost. Wax one is not worth it. It's not worth 10 times the price. You're better off just going with wax two and saving your money. Maybe having enough of wax two to last you a whole year instead of buying wax one for only a month. That can make a difference. Okay, so I think I've fully explained this one to death. Let me know, however, if you have any questions and anything that you would like me to clear up. Okay, so let's end this one.